Hello everyone, my name is Youngjuna and I'm one of the CS380 TAs, and I'm also a master's student in SGVL lab, which is led by Professor Yun. And today we're going to talk about neural radiance fields from fundamentals to applications. Okay, so before we look into NeRF, let's go through what are the target tasks and what is our input and output. So our input is images from multiple camera viewpoints, and by reconstructing 3D scene representations, and what we want is as output is a rendered images from novel viewpoints. So the novel viewpoints means a camera viewpoints which is not given as input. NeRF, or neural radiance fields, was presented at ECCV in 2020 and has since had a significant impact on the fields of computer vision and graphics. As previously seen, NeRF takes captured images from different viewpoints and synthesizes images from novel viewpoints, as you can see in this here. So the example below shows is high quality rendering and also shows very continuous and consistent 3D reconstruction results. Okay, so what kind of 3D representations do make NeRF this powerful? There are several factors that contribute to the power of NeRF, but the first thing is actually NeRF represents 3D space as an implicit representation. An implicit function or representation, just like how we describe a circle using a quadratic function, we aim to represent much more complicated 3D scenes with a neural network or MLP, like this. When given a three-dimensional location X as input, it outputs 3D representations such as the probability of the object exists in that location. So basically it's a parameterized mapping function from a location to a 3D representation. So you can think of it as a functional approximator that represents sign distance function or occupancy field of the point in the space. Here the figure on the right shows the occupancy network. You can see that the red color is inside the object, and the blue point represents there is no 3D geometry exists in the 3D space. So it is very compressive representations because we can represent a very complicated scene only with a single MLP network compared to the other explicit ones, including voxels, mesh, or point clouds. However, it is itself quite difficult to optimize, so it requires a pipeline that stably optimizes the 3D scene with a proper manner. Here we show a NeRF's way of representation. This is basically an implicit function where we take 5 the input, 3 for spatial location, x, y, z, and z, and 2 for viewing direction. Viewing direction means from which direction we are looking at the 3D space. So because we assume to know the camera extrinsics as input, as a metadata, so you can just think this is given with the input images. And the output is the 4D representation, and 3 for the RGB color or radiance field, you can say that, and 1 for the density value that indicates how dense the coordinate space is from 0 to infinity. So zero density means the space is empty, and the infinity means the point is fully opaque. So how do we learn 3D representations from 2D images? This is the method overview of NeRF. This is quite similar to the ray tracing technique in the lecture, but it's quite different. Since we have no clue where the object exists in 3D, we first cast rays from every input pixel through the 3D space. And we sample hundreds of 3D points along the ray, and this is why it is called volumetric. And we estimate the 3D representation of each point just like we talked earlier. And we can accumulate these estimated 3D points into 2D space to represent a corresponding 2D pixel color. And we can calculate the rendering loss in the 2D space, and this is a very simple way of explaining how NeRF works, but actually there are much more details here. We are not gonna go into all the details in the lecture. Instead, we are specifically focusing on how volume rendering is done. So volume rendering is actually a very classical work, even exists in the 80s in the graphics field. However, the representation is very powerful and it makes the training of NeRF very stable and reasonable. So firstly, this is basically a rendering pipeline that computes the color along the rays through the 3D space. And what we want is to estimate the color of the pixel that is casted from 2D images. So we need a mathematical mapping from a camera to ray for each pixel. And then another mapping we need is mapping function that is from camera ray to the pixel color, which learns the function the author called a planoptic function. In computer vision, we usually represent space in 3 types of coordinates: word coordinates, camera coordinates, and image coordinates. The word coordinate is a canonical coordinate which is invariant to all input camera viewpoints, and we can map these word coordinates into a camera coordinates which is defined in the specific camera space. And this can be done with the extrinsic metrics of rotation and translation. And after that, we can map the 3D camera coordinates into a 2D space by multiplying intrinsics k to get the image coordinate here. The NeRF actually is done exactly the opposite way in reversing this operation. Since we have multi-view input images, we map from 2D space to 3D camera coordinates, and we can transform this coordinate into word coordinate, and we can estimate the representation, and we back to the 2D coordinates via the volume rendering pipeline. And to sample points, we have ray origin O and we have ray direction D. And by using these 2 vectors, we can cast rays through along the 3D space, and we can sample multiple 3D points along the T. And the T decides is basically a scalar value that controls the distance along the ray. And volumetric means that we don't use a surface-based model where we deterministically know the position of the 3D geometry. Instead, we want to probabilistically model 3D space in a continuous and fully differentiable rendering model without knowing the intersection points. Okay, so what is the difference between the surface rendering and volume rendering? What we want to know is how ray intersects with the scene. In surface rendering, we know where the geometry exists because we have the explicit representation such as mesh or point clouds or something like that. And we know where the geometry exists, and we loop over the geometry and check whether the ray hits the ray or not. So what we are looping is the geometry here. Meanwhile, in volume rendering, we query geometry representation along the rays by looping over the ray points. Because so we first cast ray first, and what we are looping is the each sampled points here. So this is the difference between the surface and the volume rendering. Okay, now let's move on to the volumetric formulation for NeRF. Let's say we want to represent these colors of this cloud from these camera viewpoints here. There is a image space here, and let's say we cast rays RT, just like we saw earlier, and the ray traveling through the scene and hits a specific particle at distance t along the ray, and we want to return its color C of t. Okay, so the question is, then what does it mean for a ray to hit the volume? Hitting a volume in NeRF is kind of like a probabilistic notion. It represents the likelihood that you hit a particle within its small interval around t, and you can represent it as sigma t dt. And the sigma here is called the volume density, which is really important representation in NeRF. And another important concept here is a transmittance t of t, which indicate whether a ray survive until the point t. So to hit something at t means that we haven't hit anything fully opaque before this t. So you can interpret this transmittance term as how it was transmitted through the volume along the ray to that specific segment here. So by combining the 2 probability terms tell us how much you see the particle at t and surviving all the previous hits. And actually t of t can be calculated only using sigma here, since the transmittance is conceptually an accumulation of not hitting before t. So you can find the detailed derivation of t of t in the paper by using the Taylor expansion, and it's fully differentiable. And we simply add the color term on top of these two T of T and sigma T, and we get the expected value of color by integrating all the points on the specific segment here. And since this is a continuous representation, and there are integrals not only for the outer term here, and also the T of T itself has an integral inside the transmittance, and it's a nested integral, so it is very computationally tricky as itself. So what we do is basically approximating this nested integral by using the quadrature by splitting the ray into n segments, and each segment has a length of delta t equals ti plus 1 minus t of t. And we also assume that the volume density and the color for each interval is constant to make the computation more efficient and more attractive. And through the mathematical derivation of quadrature estimation gives this full summary of the values like this here. Actually, we skipped some mathematical parts, and if you want to take a look at those, go to this detailed derivation link, and you can check the full derivation of how we can get the alpha values here. To summarize, the expected value of the pixel color is actually a weighted sum of 3D color values, assuming a piecewise constant density and the color in each of the intervals. And we have this transmittance T of I here, which represents how much light is blocked earlier, and the alpha value, which shows how much the light is contributed by segment I. And since this is all of the volume rendering equation, you can easily see that this method is trivially differentiable with respect to color C and sigma, which represents volume density here. And I think this video shows intuitively how NeRF works. So we have images here, and we cast rays along and we sample points along the rays. And for each 3D points here, we estimate the 3D representations, color and volume density by using the very lightweight MLP here. And actually, we skipped the how do we sample these 3D points, but you can just think of it as a uniform sampling. And after we estimate the color of these 3D points here, we can accumulate these 3D points by using the rendering equation just we saw earlier to estimate the 2D pixel points here. And we are casting rays for each pixel and for each cameras, so we can densely reconstruct this 3D representation with the high quality, just like this. Okay, so this is the results of the rendered 2D images by NeRF. And as you can see here, since we take not only 3D locations as input, but also we take the view directions as consideration, we can synthesize the view dependency effects by adjusting the view direction values. And this is pretty impressive results. And actually, I've introduced some of the intuitive concept of how NeRF's representation and rendering works, but there are a lot of details in it, such as how do we sample points, or positional embedding, or the architectural details. So I recommend you to take your own time to look at the ECCV 2022 tutorials on NeRF volumetric rendering for computer vision if you're interested. And also the website called radiancefields.com has a lot of state-of-the-art radiance fields research. So visit the website, and you could feel how NeRF has changed the research field and the amazing capability of them by reading the recent techniques. And another good resource that I want to recommend you to take a look at is called NeRF Studio, which is an open source software designed to simplify working with NeRF or NeRF variants. It is super user-friendly and easy to use, so you can play with your own custom data sets, and you can reconstruct your own room or somewhere you want to reconstruct. And it is very interactive viewer, so I think you can easily play with it. NeRF has emerged as a groundbreaking method in synthesizing 3D scene from 2D images, yet there are a lot of limitations and the applications by using NeRF. While NeRF shows a good rendering quality and reconstruction, there are several limitations in tons of papers that have tried to overcome those limitations and utilize this for various applications. One of the key limitations is the rendering and optimization speed. Secondly, original NeRF models were limited by the assumption of the static scenes. And the another problem is that the NeRF requires per scene optimization, where we have to optimize for each scene independently, meaning that we cannot exploit the large datasets prior. And the fourth one is the original NeRF do not explicitly create mesh structures, which are important for many 3D applications. So some research moved towards technique in surface reconstruction to convert NeRF output into usable 3D models. These are the very few limitations and applications of NeRF. Actually, NeRF has been cited more than 6,800 times, so the list goes on and on, actually. In this talk, we briefly introduce a few examples here. To enable the fast optimization and rendering, there is a paper called PlanXL, which is accepted at CVPR 2022. In PlanXL, to render a pixel, we intersect its ray with voxels, explicit voxels in the model. Each stores opacity and spherical harmonics coefficients, and they evaluate the planoptic function at regular intervals along the ray using trilinear interpolation of the neighboring voxel coefficients. The ray color is determined by combining the sampled values according to the volume rendering formula. And the overall pipeline looks just like NeRF, but it has explicit voxels in it, and that could be optimized to the scene within a couple of minutes. And since we're only fitting voxel parameters, we don't use any neural network involved at all. So it makes the optimization pretty fast, and it shows that, and also shows that pretty good quality. And the word we capture is usually dynamic, or the objects are deformable. We want to capture the driving cars, or a dancing person, or a man on the horse. However, the original NeRF assumed that the scene we are capturing is time invariant or static. So it becomes a huge direction in NeRF, usually called dynamic scene reconstruction or dynamic NeRF. So a simple solution is to add time dimension on top of the original NeRF input and expect a neural network to estimate the time variant colors and densities. However, since the problem is super under-constrained and it usually requires simultaneous multiple viewpoints in the camera dorm, so it is very challenging to directly apply this kind of format into to the original vanilla NeRF. Another good approach is to use a deformation network, where we not directly input camera coordinates or word coordinates to the MLP itself to get the color and density. Instead, we first transform the coordinate into canonical space with the deformation network, and then we query color and density from this canonical frame with NeRF MLP, making the problem much more constrained. It seems nice because we can model the 3D flow and we can read out the consistent canonical frame. However, it is still an under-constrained problem. Dynamic NeRF, or DNeRF, is a primary model which utilizes deformation network, and it actually works very well under synthetic datasets or small objects, but it does not perform well in the wild datasets, where we usually capture monocular video or real-world scenes. So there are tons of papers that tries to overcome this kind of limitations, and since then numerous papers have proposed dynamic NeRF that can apply to real-world environments, and they can now be easily applied to real-world videos. However, it is very slow to optimize a dynamic scene, which takes hours or even days to obtain high fidelity results. But the results looks really good. Another direction comes from the limitation of NeRF that it requires per scene optimization and cannot utilize a large dataset prior. So many researchers have proposed a generalizable method with prior knowledge. And as NeRF originally learns scene-specific representation, so it is difficult to generalize to other unseen scenes. Unseen scenes means that the data sets which are not in the training data, in the training set. And secondly, if the input camera viewpoints getting sparse, for example, let's say we have only 3 images as input, the reconstruction results is very unsatisfactory. We generally call these two properties as not generalizable. It means that it cannot share representations across scenes or views. So Pixel NeRF achieves a one-shot single view reconstruction even without any test time optimization. So the key idea is to utilize image features as NeRF input with a large data set. It enables few-shot cases, and other papers such as IBRNet or MVS NeRF achieves a few-shot inference as well. The right figure shows the results of the IBRNet. It shows very good results. However, it is still very challenging to reconstruct unseen space like backside of the scene because we don't know what could possibly look like, and it makes the problem extremely ill-posed. So some papers actually use the generative power to reconstruct the backside of the object with a very large generative priors. Another direction is extracting surface from NeRF. So if we want to extract the surface with NeRF's volume density, we can threshold with a constant thresholding value C. As you can see here, if we threshold with low value, then the surface is not clear because the background could be included as a surface. So, however, with the high thresholding value, most of the surface could be removed. So it is quite ambiguous to find the proper thresholding value in original NeRF's representation. So this is because there are no explicit definition of surface, because the density itself does not shows any guarantee that the surface should be the specific number, and this makes the extracted surface not that satisfactory. So to solve this issue, researchers combine NeRF with sign distance function or SDF, which make the MLP to learn SDF field as a scene representation. So what's the definition of the sign distance function? The definition says it's the minimum distance to the closest surface with the sign. In this figure, in this figure here, the black curve omega represents the surface. The inner points of the surface has negative values with the distance, and the point in the outer part has positive value with the distance as well. And we can define the surface as a level set where the function values are 0, or you can call it a 0 level set. And as in the right figure, the SDF modeling enables extracting much sharper surface of the scene or objects. So what we do is that basically the input is pretty the same, and by using the MLP, we are not estimating the volume density here, but instead we estimate the SDF, which has more powerful definition of surface. Okay, so I'd like to introduce one of the papers in our lab that's published this year. And the paper is titled as UFO Recon, Generalizable Sparse View Surface Reconstruction from Arbitrary and Unfavorable Sets. So the target task of this paper is generalizable surface reconstruction, where we take a few shot input images, and we want to estimate the underlying geometry or surface of the objects or scene. However, most existing methods commonly make one critical assumption, which we call the optimal view set assumption. So they assume that the input images always come from an optimally fixed view. In other words, while the scene to be reconstructed during training or testing can be continually changing, it is assumed that the camera configuration remains fixed, favorable for the reconstruction. So as you can see in this left figure, the input camera configuration has a very limited transformation and rotations, and input views has a large overlap between images. Therefore, if an arbitrary test set that was not seen during the training process is introduced, let's say we have a large transformation and rotations here, so it leads to the problem of the method not working properly for the baseline. To verify this, we tested with a state-of-the-art model called VolRecon with both best view set and an unfavorable view set as input. And we can observe that a drastic performance degradation when using the unfavorable set, as you can see in this right figure. And also the estimated depth looks severely degraded as well. And we call this property as not view combination generalizable. However, if we think about the practical inference scenario, we cannot always guarantee the optimal view sets as input because the view sets in the training time is not identical to the view sets in the inference time because we take captures from a random viewpoints. So we should reconstruct a faithful geometry from any kinds of camera configurations as input. And we call this property as view combination generalizability. And we want to achieve a more generalizable method by combining the scene and viewpoints and view combination generalizability. To achieve this, we believe that it is important to effectively model the correlation between input images. So no matter which types of view combination is taken as input, such as blue cameras in the left or the yellow cameras on the right, having a good combination prior becomes important for the view combination generalizability. And to this end, we aim to model the relationships between the images and use this as a kind of robust correlation prior. So firstly, while baseline methods extract features from each image independently using CNNs, we choose to use a transformer based on cross-attention to take into account the relationships between all the possible input image pairs. This approach allows us to extract features by considering the relationships among all input images. And secondly, we address the modeling of global correlations between images. After extracting the features using the cross-attention transformer, we align all the features to a single view by transforming the other views into a designated reference view by using the homography warping. And subsequently, we create a feature correlation volume by using the dot product between the reference view and the others. And we can then process this correlation volume using the 3D units here. And finally, we get the global cross-view features, which contains the global correlations among the source input images. Okay, so this is the overall pipeline of the UFO recon. To summarize this work, it is important to model the relationship between the source images by not only using the by modeling the global correlations and using the cross-view matching transformer, and we additionally extract the similarity between the pairwise input features, and by aggregate all the features from these pipelines, and the reconstruction transformer use the self-attention to process the extracted features and estimate the SDF representation and also the color representation here, and by using the alpha blending here, and we volume render the 2D images, and we calculate the 2D loss here, and we backpropagate all the gradients into the backbone networks. So this is the results of the UFO recon and the comparison with the VolRecon, which is published at CVPR 2023. As you can see here, the input images are unfavorable source views, where the transformation and the rotations are quite large compared to the favorable source views. And as you can see here, the reconstruction quality of the VolRecon is pretty bad. And compared to this baseline, our method stably reconstruct the 3D geometry with the unfavorable source views, while the training data sets are identical to the base VolRecon. And we actually also do the random set training, where in the training process, we take the random set of camera configurations as input, and we use that input to every single iterations, and we can expect the model to handle any kind of arbitrary inputs as input. And this is the another results. As you can see here, we compare with the three types of input: favorable sets, and normal set, and unfavorable sets. And we use the metric chamfer distance here, and chamfer distance, the lower the better. And as you can see in the favorable sets, it is quite similar the reconstruction quality with the baselines and hours are not that huge. So, however, if we test with the normal set, the performance degradation already happens in the baseline methods, while our method faithfully reconstructs the geometry pretty well. And if we go into the unfavorable sets, the Volrecon and RTR, the baselines severely degrades when the inputs are really severely unfavorable, while our method still robustly reconstructs the underlying geometry pretty well. So yeah, so these are the results, and now we want to take a look at radiance fields with the generative models, and actually combining these two independent branches, generative models and radiance fields, is a very interesting one. So I like to introduce as a final topic. So this is the results of the Dream Fusion, one of the important papers in the generative models combining NeRF. So it is quite impressive that the consistency between the viewpoint directions and these images are not exist in the data sets, and the generative power is pretty impressive here. So this is the combination of the foundation models in the 2D image data sets and the NeRF representation. So another example is called sign, which is very impressive here. So we have the input 3D representations, and we want to move hands, or we can replace the texture here, and we can also the stretching the back like this, and this kind of the editing based on the text input. Or we can also make this realistic scene into a shining diamond vase deck, and we can also manipulate the source views into a silver round table by inputting the text prompt based editing. And another interesting direction is semantic editing, which we edit the composition of the 3D geometry here like this. And also we can change the color, as we saw, just like we saw earlier. It's quite slow. And also the conference room results. We can change the color of the floor here. Okay, so the next thing is manipulating capture scenes, or we can call this as a stylization. And this is from the paper called Artistic Radiance Fields. We combine the 2D images with the style, and we put the style into the 3D scenes, and the results looks pretty consistent and also very interesting. And we can also input the cartoon as input, and we can make the real 3D scenes into a cartoonistic 3D representation. This is another result, and the left bottom side is this tile. I think this type of manipulation is especially interesting in the VR AR application, because we can not only capture the our realistic scene, but also we can synthesize the artistic scenes that we want. So the radiance fields is still an important topic in 2024. In particular, various hybrid representations have been proposed to make NeRF's slow rendering speed real time, and among them, Gaussian splatting is drawing the huge attention of researchers. So if you're interested about this, I have attached the link here, short video and long video that introduces to Gaussian splatting, what Gaussian splatting is. So it'll be good to check it out yourself. And this is pretty much for today's talk, and thank you for listening.